So welcome. My name's Judith Canner. I'm a professor in the Math and Statistics department, and I'm also the Quantitative Reasoning Assessment Coordinator for the university. And so I have a very deep passion for making sure students know how to interpret quantitative information because they are absolutely inundated with it every day, especially through social media. And I don't think they always know how to ask the right questions to actually evaluate that evidence. So the goal for today is to kind of think broadly about why we want to teach with data using quantitative information in our classrooms regardless of where we teach, how we want to teach in our specific classrooms, and then we'll narrow in even further to how do we help students learn how to analyze quantitative information. But more follow-up, like I said, I'm the quantitative reasoning coordinator, so I am here as a resource as well. As I mentioned, we're going to kind of go in narrow in. First, I don't think I need to sell you that teaching with data is important, but I will anyway. So you can take that and sell it to your colleagues. And then I really want to engage you and think about how you, in your classrooms, how you want to teach with data. And I'm using the word data because data, I think, is one of those words that's thrown around a lot and can mean a lot of different things, and it's a little less scary than quantitative evidence. So that's why I'm using the word data. And then narrowing it even further, how do we engage students with data in a way where, in some of our classes, maybe we are teaching mathematical methods or statistical methods, but in a lot of our classes we're not. We're relying on either previous information or simply their critical thinking ability. And so I'm going to give you a couple different frameworks for looking at that, including how to review academic articles, newspaper articles, and also I call it a quick and dirty list of questions you can ask to make sure you're not getting fooled, as you said. So after we think about how we're going to engage, the other thing we have to think about is what research strategies do we want students to use. Now again, I said I wasn't going to teach you any math or statistics. So the approach I'm going to take here is really getting the students to think about the fact that all evidence is not created equal. So that is something that they need to know. So there's different kinds of evidence, from experimentation, observation, making types of comparisons, modeling. Depends on your field. I've given some basic definitions here. And then also there's ethics and practice involved with each of those. And so one thing that some areas do is they've created these hierarchies of evidence. So I'm going to go through just a few examples to show you. And they aren't in here, but I will post. They aren't in the outline because they're images, but the PowerPoint will be posted, so you'll get access to this. So this is an example of a healthcare-related hierarchy of evidence for intervention studies. So intervention studies are used like in nursing, healthcare, social work, that kind of thing. And so what it's done is it's listed the types of evidence in rank, the number 1 being the best, if you will, and number 7 being the least, having the least amount of strength or support as far as evidence. So expert opinion, or consensus is the lowest type of evidence, which is a really important thing for students to recognize, that just because someone who's an expert says it doesn't mean it's actually right. Somehow we've allowed education to automatically mean expertise, and there's a whole bunch of people out there who are talking like they're experts in an area, and they don't even study that area. So, really getting them to think about it. Qualitative or descriptive studies, helping them understand that if it's just a description, that is evidence, but it's not as strong as, say, a systematic review of a bunch of descriptive studies where they've noticed a trend after reviewing lots and lots of descriptive studies. And then we get into the more specific types of almost moving into experimental, very specific case-controlled cohort studies, controlled trials, randomized trials, and then finally a systematic or meta-analysis, which would review all of those case studies. So this is an example of one I found in healthcare. Here's one more specific to biomedical research, and the way they've structured it is, again, systematic reviews and meta-analysis pretty much is always the top, because it really is an analysis of an analysis. and controlled studies, and then all the way down to, test tube and animal research, while important, is recognized as not being the definitive answer on human health in biomedical research, but it is a starting point, and the way they've structured it like this is, it's a foundation that you then build on to get to that pinnacle of the system reviews and meta-analysis. Here's another example of a hierarchy I found for social sciences: case reports, starting at the bottom, and again moving up through cross-sectional surveys, case control studies, cohorts, and then moving into experiments, systematic review. And the things to recognize for this is that, students might be, well, oh, it's not a controlled trial. Well, ethically, you can't always have a controlled trial. So we really want the students to understand that the evidence they're evaluating may not be high on the hierarchy, but it also may be the best that we can do given the ethical considerations of the situation. And so that balance of ethic and hierarchy of evidence needs to be...
But I think the other piece of this is also, how are you using the evidence?
Yes.
Right? What kinds of claims can you make from the evidence? How generalizable is it? Because these scales are all assuming that generalizable evidence is the highest and best.
And the best, yes.
And also assuming that conclusions can be generalized.
Yes, and we'll be moving into some of those things a little more specifically. So here's a few more. I actually found some instructions, sort of a hierarchy for, or a rating, if you will, for evaluating qualitative evidence, if that is more your field. And then I even found, this isn't really a hierarchy of evidence so much as a quantitative way of evaluating qualitative it's actually source credibility when it's communication, so someone writing. So this might not even be a necessarily quantitative piece of evidence, but this is just an example of evaluating source credibility by the person by rating these scales. And the reason some are bolded and some are not, I put the reference here, is because you add up the way you score these things. There's 3 ways you score based on the credibility of the communication that you're reading, and then you put that together to sort of get an overview. And so this isn't, it's a way for the students themselves to actually start to evaluate evidence. And this, in this case, is not actually quantitative evidence, but could be interesting. I didn't know exactly what the crowd was going to be here today. So thinking about that, and we are going to get more into, okay, once you've figured out that level of evidence, you still have to actually evaluate the evidence to test for generalizability, even if it is a systems analysis or meta-analysis. Doesn't automatically mean it's the best, but we do want to make sure students understand within our field what the hierarchy of evidence really is. And so I've presented a few examples, but I'm curious for your different fields, how you would structure or present evidence to students. Like, do you present everything at the same level of authority? Or do you help students understand, how do you model for students that this case study, while very relevant, foundational to the field, was not what led us to now have cognitive behavioral therapy today. It's, this was a case study that started the process of gathering evidence to support, for instance, cognitive behavioral therapy as a form of very effective evidence-based practice for treating PTSD and things like that. So that understanding of how evidence works and how you're presenting the evidence, and then also, do you have a hierarchy of evidence for your field? Or maybe you need to create one. So I thought that would be, we're a little bit behind on time here, but maybe just take a few minutes and try to think on your own, like, what would be the hierarchy of evidence in my field, and then how am I going to explain this to students? How will I teach this or model this to my classroom? Because you get to speak in English. But again, so this hierarchy of evidence, maybe it's not so much a hierarchy for your field. It could also, some disciplines actually created frameworks of like checklists and things like that for their particular disciplines on how to evaluate things, and I'm going to give you some frameworks for how you could create some checklists in different situations as well. So as we kind of go through this last part of engaging students with data in our classroom, the last thing is to think about the types of data that you could engage them with. So you can have raw processed data, data from research studies, simulations or models where you've created data from a situation, data from civic partners, data generated by students. But again, all of these would be in raw form, so I would have to teach you math. So what I'm going to focus on is the last two, what I'm going to call processed published research data. So if you aren't getting the raw data, although a lot of times, and more journals are doing this, where they're actually making the data available so that people can analyze it further. But academic articles and media, I think, are probably the two most common forms of that processed, published data that's out there. And often the media is a processing of the academic articles themselves. And so that's another piece of the pie to think about for the students as they engage with the data from these sources. So thinking about that, we've kind of talked a little bit about where this is coming from, data that might be collected, data, situations where they're already engaging in, solving problems with numbers and quantitative information, and then synthesizing information from multiple sources. I put this little resource on here. It's called Data Counts, and it's just tons of different activities about engaging your students with different kinds of data. So that's an available resource for you. Speaking of Stat 100, just so you know, if your students do take Stat 100, the very technical process, this is everything that they should know, in theory, right? What they actually remember is another question, and what's scaffolded and throughout their courses is something else. But they should have at least a basic, in Stat 100, they should get a basic understanding of what is necessary for a good study versus a study that's not good. And also an appreciation for trustworthiness of a study versus the certainty of a study, which are two different things to consider. And I'm going to mention those a little more later. So thinking about that side, how to engage students without teaching them math, because that was my promise, I take what I call a Socratic approach. It's kind of maybe a bastardized version of the Socratic approach, but the Socratic method, right, is you ask questions. You keep asking questions, and then you ask questions about questions. So I can just to give you an idea, if you haven't heard of this approach, people have generalized sort of 6 types of Socratic questions: questions of clarification, questions of assumptions, reason and evidence, viewpoints and perspective, implications and consequences, and then questions about the questions themselves. And I will argue that all of these questions can then be taken and adapted to help students understand how to question quantitative evidence. And I think that really is one of the best approaches for helping students evaluate quantitative evidence, is we can ask them questions, or they can ask questions themselves, and even if they don't have a full understanding of all the details of calculation and statistical method and evaluation, they can ask enough broad questions to really be able to evaluate evidence on their own, even without a very rigorous background in statistics. So I'm going to kind of go through an outline of questions, and I gave the outline to you of the notes, so they should all be in there. So I'm going to go through this a little quickly because I want to get to an activity and then a framework for making this more maybe accessible to students. So research questions, so what is the research question? Is it relevant? Is it meaningful? Is this research question even one that can be answered? It's a good question to ask. Is it even relevant to my field? Is it adding anything new to the field? What type of research questions? Are they evaluating a program? Are they looking at how often something happens? Are they looking at trying to test cause and effect? These are the types of questions that we should ask about research questions within this. And this is very much in the framework of an academic article and what they might expect to see. Then you go into the data collection methods, which we've talked about. Was the design appropriate? Are there sources of bias or issues of validity within how the data was collected? What type of data collection method was used? Because if they paid attention in Stat 100, they should know that experimental data is really the only one in which we can verify cause and effect. Observational data, you cannot verify cause and effect, although it can help you explore where cause and effect might be happening. And there are standards of evidence for using observational data and assessing cause and effect as well. Protocols, sample size is a big one. Like how big was the sample? Was the sample size appropriate? Could you have gotten a bigger sample? You know, there are limitations to sample size, so helping them understand, asking that question. Then data exploration and analysis. Was this a case study? Is this exploratory data or confirmatory? And having the students make that distinction, because both are valid forms of research, but exploratory is exploring ideas to get to the research question, whereas confirmatory is starting with the research question and evaluating it and testing it. So those two processes need to be understood in both validity and purpose if you're synthesizing information. And then, of course, you can get into the more technical, which they may or may not be able to fully evaluate, depends on what level of training they've had. But they should be able to at least look at summary statistics and tables and graphics and look at that and use that information to be able to interpret and analyze the information presented, and to also evaluate whether or not they're good representations of data. And we're going to talk a little bit about representation of data in a bit with an activity. And then inferences. Do the data justify the conclusions? Conflicts of interest, unanswered questions, and then generalizability, right? That's the last part. So that's a lot of questions for students to kind of go through, and especially if they're doing a research paper or a project where they have to combine lots of sources, it might help for them to have a framework. And because they need to understand sort of these things. If they're going to use a study as evidence, they need to trust its design first, understand its original intent, understand its limitations, and that goes back partly to the hierarchy of evidence, but also just in general, limitations and assumptions, and then understand its level of certainty. And that even though, you know, with a small sample size, it doesn't mean the study's bad because the sample size is small, it just means that your level of certainty might be lower in your conclusions. And so having that understanding about how to evaluate evidence. And so what I've adapted here, I've actually adapted this, nursing, I must say, has really been doing a lot with evaluating quantitative evidence for their nursing students. So there was a lot of really rich materials out there for healthcare and nursing programs on how to get their nurses to evaluate evidence. And so this was adapted, and I gave you a handout that kind of has the framework provided for you to help students organize and synthesize the evidence as they go along. So each category or column has a title that really relates back to all of these questions that I've just went through. From, you know, okay, of course you put your citation, that's just for record keeping. Then you outline the conceptual framework. What is the research question and the theoretical framework? Why is this study even being done in the first place? What is its purpose? And then the design and method of collection, you know, and this could be, depending on the level of your students, them just recognizing it's observational versus experimental. But as they get more sophisticated in their understandings of types of evidence, they might be able to recognize more types of design that are especially relevant to your fields. Sample size, what types of groups, who were included in the studies, was it people, was it plants, was it, you know, was it animals, was it rivers, you know, what were the things that were actually being studied, how many were being studied, a description of them, what is the sample size. The major variables studied and how they are defined so that they understand, you know, especially if it's a cause and effect situation. What was measured and how. How these variables were measured is another question. You know, I'm sure in environmental sciences you have, I remember taking, you know, kids, I used to do environmental summer camps, and we would take the students out and they would catch little tiny invertebrates in rivers, and then they would catalog them, and based on what was visible in the river, they could determine if the river was healthy or not. And that was using quantitative by counting and observing, like that's quantitative evidence. But that measurement was, you know, the measurement that we were using was identifying a species, which sounds kind of weird. In other situations, it might be a more specific kind of measurement that is being used, like from anything from like a clinical method to a type of survey to a type of, you know, interview method or style. So it can really vary depending on the field that you're in. But how are these things being measured? How were they analyzed? What are the descriptives and the conclusions? And here, this is where, again, I kept debating back and forth on whether or not I wanted to go into all the statistical fallacies in interpretation, like a p-value versus a confidence level. And ultimately, I decided I would leave it out because in the end, you know, students, it's good for students to understand that, but often when they're reading a newspaper article, anyway, that's not going to be reported. Yeah, so I just chose not to go into that, but I'm happy to talk about how we can help our students understand those difficult concepts that are reported often in scientific articles, so that those can be better understood. And then, of course, the findings, and then the appraisal of its worth. That, again, is based on how the study was even done and designed, but also that hierarchy of evidence can be brought in as well. And so this sort of table of evaluation, which I printed out for you and kind of created into a grid that you can adapt to your field, to your specific situation, to hopefully help students organize information. And you know, I know a lot of students, they do annotated bibliographies. I might argue that this is a better structure than an annotated bibliography because it really helps them organize the evidence in a way where they're synthesizing it and structurally analyzing it, instead of just broad paragraphs about
Can I just report how happy I am? Because right after spring break, I was about to make my students do an annotation. I'm pretty psyched.
Awesome. I'm glad. Yay.
You know, to send an electronic version.
Yes. Yes. All of this will be
That'd be
sent out
brilliant,
in
yeah.
the presentation, everything will be made available in a drive for you guys afterwards, so don't worry. So that's evaluation of our academic articles. And I'll show you one maybe a little later. So what about media sources? So lots of questions up here, including some examples to think about. And I'm going to give you the quick and dirty, as I call it, method of asking these same questions. But things as basic of what kinds of numbers are involved, what are the magnitudes? Are they reporting rate of change or absolute change? That's a really common thing. And proportional reasoning is one of the most valuable skills someone can have, and is also maybe often very neglected. And so that understanding, can claims be checked, right? You know, I don't trust newspaper articles that don't link me to original studies or to the data that they used. I just don't. Especially now in the age of the internet where everything can be linked. You know, asking questions, some very basic questions about causation. Is this a causative or is it a correlative study? And then the graphics themselves, that's a really big thing which we're going to look at. And again, we'll make this available, but and it's in your outline as well. The other side of things, you know, just to kind of take them through a process is, and you could even turn this into a grid if you wanted to, like the other evidence, you know, asking sort of these what if questions. Well, what if this was done instead, or what if they asked this question? You know, one of my favorite things to ask students is, what if instead of saying, you know, do you like chocolate ice cream, yes or no, you said yes, no, maybe, right? Or like, or are you going to vote for a certain candidate, yes or no? What if you said added a maybe in there? Like that changes a lot of things to add that maybe as an option. So thinking about what if you did it a different way. Interpreting the magnitude of quantity, and thinking about these processes. And so this might be something you sort of have students, either you model or take them through as a process to think about the evidence presented in news articles. And then here's the quick and dirty guide. Sample, is it biased? Sample size, too small. Just statistics, are they appropriate? Are they what's meaningful? Is it practically meaningful? Statistical significance is thrown around a lot, but I can find anything statistically significant if I have a big enough sample size. And it doesn't mean that the difference is practical. So that's something to get them to think about. Are the graphics misleading? Do the results actually support the claims? Sometimes they attach results to claims that doesn't even go together. And then is it a truly causative effect? And there's this great book written in the 50s and it's still popular today, called How to Lie with Statistics. I have a copy somewhere, but I cannot find my copy. How to Lie with Statistics.
I have a copy.
I have a copy. I don't know where it went. I think I lent it to somebody. I haven't got it back. But it's just really simple things that you can present to students, and it's still applicable to today to help them think about how the news presents things. I also have, so there's this guy, John Allen Paulos, who wrote several books on numeracy back in the 90s, early 90s. So people have been talking about it for a long time. And then he also wrote this book, A Mathematician Reads the Newspaper. He also has a TEDx talk. And again, this was written in the 90s, and so it's talking about the Iraq War as in the first Iraq War. So the examples may not be as relevant, but the ideas are still there. And so these are some examples of ways that you can think about engaging students and having them ask those critical questions about newspaper. John Allen Paulos, and I'm happy to lend these out to people as well.
And there's also a book called How to Lie with Maps. That's
Oh.
really good. Yeah.
That would
That's
be really
cool.
interesting. So that's the sort of quick and dirty guide to evaluating evidence. And so I thought it would be fun if we went into this. And so in your handouts, you should have 2 newspaper articles, actually. The first one we're going to look at is this 4 U.S. men, 40 years of falling income. And so here's the main graph here. That's sort of what I want to zero in on. But this author took information from earnings in the U.S. From the U.S. Census and the Bureau of Labor and Statistics and the American Communities Survey, which are all regularly done analysis of and it looked at compared 1972 to 2012, and then split annual income, the median annual income, by 3 different age groups, and demonstrated that there is a sharp decline. So take a minute, think about this. So just looking at this graphic, what are some things that you notice at first?
Well, I can't tell you.
35 to 44 decline.
So 35
to 54.
Yeah, okay. So we see a decline. So yeah, this is Census Bureau. So this is pretty comprehensive data. So parochial sample size.
It's all in constant dollars.
It's all in constant dollars. So I think he claimed adjustment for inflation.
Well,
That's how you make
Yes,
it
so constant dollars.
$2,012.
Yes. So yeah.
It's absolute instead of percentage.
Yeah. Yep. So he only included 1972 and 2012.
There's only 2 data points?
There's only 2 data points.
And each row straight line between them.
Exactly. And each 2 data points, that's a mathematical axiom. You need 2 data, you
Right.
need 2 points to draw a line, right? Do you think that's what wage looks like? Do you think it's a straight line when you think about wages in America? Do you think it's always a steady decline, or would it go up, go down, go up, go down?
I would expect fluctuation.
Yeah, you might expect fluctuation. Also, why did he start in 1972? What were wages like before 1972? Right. Also, the fact that he starts at $32,000 on the y-axis might make the appearance a little more steep than otherwise. So let's look at another guy who said, no, I'm not buying it. So, and he actually titled his little blog post Misleading with Statistics. So he took this graph and he started going through the same things. First of all, 2 data points. So he took it from 1972 to 2012 and he added in all the in-between years. And this is what the graph looks like now. So you can see certain things happening, like in certain eras there are higher wages, in certain eras there are lower wages. We see, the lovely decline that happened in 2008 up here and there. Plus, you also see the lovely decline that happened in the early 80s when people were lining up for gasoline. And, you know, different things that happened, and then you see rises in wages, and like, so it's fluctuating, right? It's not 2 data points. And when you look at it this way, it doesn't necessarily look that drastic, as opposed to, although it is still declining, don't get me, but it doesn't look as drastic. So then he took it a little further, and he scaled it from 0. So by changing the axis, right now it doesn't look, it's still, again, yes, it is less, it's declining, but it doesn't look as drastic as it did before. And then the last thing he did was, he said, why did he start at, so here's what the slopes would look like if you put it on the different axis, if that helps, from 1972 to 2012, ignoring the variation.
But did he make an argument for why start at 0?
So you don't always have to start at 0. That's true. The starting at 0 thing is something people recommend, but it's not necessary. And it's more just thinking, so thinking about when to start at 0 versus when not to start at 0 has more to do with what are you, what are you getting across if you don't start at 0? So if you show a bar plot, and you know the difference between the heights of the bars is, you know, 1 point, but you scale your axis so it looks like it's huge, then you are actively misleading your reader. But if you scale it correctly and show that it's not really a big difference, so it's really how it comes down to, will this actively mislead my reader based on how you scale your axis? But then he decided to go back further, because there's actually data all the way back to 1947. And when you go back to 1947, the fact that, yeah, okay, wages are declining in the last, you know, 40 years.
There's a peak in 72. Yeah.
Yeah. 72 was the high year. So saying that it's declining from 72, well, 72 is also the peak. And so he then makes the joke, well, here I did mine from 1947 to 2012. Look, wages are increasing, yay! You know. But the point is making sure that students don't just look at a graphic and say, here's the graphic, this is it. Really having them critically evaluate a graphic or visualization, and to think about how they're creating their own visualizations too, is important. And there's great, if you want to find examples, you can Google just bad graphics, and there's like a whole website devoted to it. Not to pick on anyone, but Fox News has a lot of great examples like this. Although, you know, MSNBC has its own number too.
Sure.
So, but the point is we tend to look at things and be like, oh, and we need to critically think about, well, why? Why this number? Why did he start there? Why only 2 data points? Why that axis? You know, what else is going on? Is there variation?
Well, even
asking these
whether or
questions.
not the author has already answered those questions,
Yeah.
or chooses not to.
Yeah.
That's true. Yeah. So that's just a little example, and it's something you can share with your students that's very accessible for them. To just spark that thought process behind how data is represented to them. So another study example that I wanted to share with you is this New York Times article, which I subscribe to the New York Times, so that's my, I guess I should say, I like the New York Times generally. But here, this is a study that was produced about a year ago, not even a year ago, I guess, where they linked air pollution to about 1.6 million deaths per year in China. And this was the New York Times headline, but then if you read that first line, China, about 1.6 million people in China every year, or about 4,400 people a day, according to a newly released scientific paper. That 4,400 people a day is what became the headline almost everywhere else. Even though this idea of dividing by day is not necessarily meaningful or useful, but it's just a way of making the magnitude sound big. Right? But then here's where we want to take our students through some of these questions. Order of magnitude, 1.6 million deaths per year in the context of China's population. What is China's total population? billion, it's about 1.35 billion. So in the context of the total population, this means that pollution is killing less than 1% of the Chinese population.
And what is that compared to the US population?
Yeah. Now, take that though, and then think about, well, how many people are actually dying in China? So China's death rate is about 7 per 1,000, which is very high. And so then when you start thinking about that, how many people are actually dying? I did some calculations on this, and when you look at it that way, that's 1.6 million actually accounts for about 16% of the deaths in China. Right, so that's part of the process, having the students go through that, and that's very simple arithmetic that they can go through and think about the magnitude of the numbers being presented to them. The national debt is a really good example of that. You know, how would people respond if instead of 13 trillion, you described it as, 13, now I have to do the conversions, 13,000 billion, or 1,300 billion, or 13,000 million, or when you start to take the order of magnitude, 13 trillion, and put it into terms that we understand better, like billion or million or thousands, then you really start to understand magnitude, and that can really help them get their head around it. Because 13 trillion doesn't sound like a lot. Actually, I think our debt's more like 20 trillion now, but that's just an example.
Yeah. So I like showing them the national debt clock because the fact that it's moving, that they can see it,
Yeah.
shocks them to begin with.
But it's not a steady number.
Yeah.
So the other side of this whole thing, right, is this is processed information sent to the students, and we want them to look into the context of the data. Where did this come from? How did they even figure this out? So here's, on a death certificate, does a coroner write death by pollution? No, right?
No, I can't read Chinese, so.
Yeah. So no, he does not, or she does not. So what would they look for to try to connect these things back to pollution?
Emphysema.
Emphysema, okay. Yeah, but that could be, and China has one of the highest rates of smoking too.
So some.
Asthma?
Yeah.
Asthma, but can also be connected back to smoking too.
Cancer.
Cancer, types of cancer, yeah. Types of cancer, which again, sometimes can be connected back to smoking. So that's what a confounding variable. The fact that China does have terrible air pollution, don't get me wrong, but it also has one of the highest rates of smoking in the world, and so those two things are confounding, which could lead to these deaths that might be attributed to either one, and we really can't separate this out. So it's something to recognize about the limitations of this study and this number. So even if they looked and found 1.6 million deaths attributed to emphysema, asthma, types of lung cancer, maybe some other types of cancer, that would be really difficult.
Oh, and in their abstract, they say the air pollution is calculated to contribute to 1.6
So
million deaths.
I gave you the abstract of the original paper as well. So you can see this is where we can take students back and have them actually look at it. Now, this paper might actually scare students. The abstract's not too scary. But as I scroll down, they have some mapping. Here is what they started to do to try to figure out what was connected to pollution and what might have been connected to other things. So they couldn't obviously count how many deaths were related to pollution. They came up with a model to help them estimate how many of the deaths they observed, of those, what would be attributable to pollution. And so the soundness of the paper is not something that I'm questioning, but how it's being reported and how it's being used is something that might lead to some questioning. And so we always want to take students back to the original source when possible, and also just have them think about the logic behind that and the limitations. No, we don't know that exactly 1.6 million people are dying of pollution in China every year. What we do know is that based on these ideas connected together, confounded with some of these other things like smoking, that we could estimate maybe 1.6 million people are dying every year, which is about 17% of the total population. or not the total population, the total number of deaths every year. So it's understanding the limitations and how you phrase. It's not the statistic that lies, it's the words that are surrounding the statistic that are lying. So getting students to really think about these ideas. And again, you can keep it very simple, or you can go and that whole long list of ideas and exercises and questions and have them go through those structures, or even create checklists for them. So I'm going to end with a few last minute pieces of advice. The first thing I would say is model good behavior, demonstrate your critical evaluation of data presented in class, and guide students in critical evaluation of data. Here's a few examples. If I ask my class, what is a healthy human body temperature, they say 98.6 degrees Fahrenheit. But really, and I do this in my statistics class, it's not. That number came from a study done 150 years ago, more than 150 years ago now. This is around the time of Lincoln, with mercury thermometers that took about 20 minutes to read. And also, your body temperature varies across your body during the day. It can vary just from emotional state, level of stress, like 98.6, anytime a number's too precise, tell students to question it, you know. And then other examples, there was, this was a big one, and Time magazine had this on their front page in the 90s, that 150,000 women die of eating disorders each year. Okay, actually that year only 57,000 women in the United States died at all. So how did they get this number? Well, it was a bastardized statistic. There was an estimate from a study that 150,000 women had eating disorders.
Oh no.
And then that was taken and reported as number of deaths per year. And this was the front of Time magazine. So that's something, and there's numbers like this that get thrown around all the time that are from outdated studies. And so helping students model that even when something's commonly accepted, it may not be correct, and modeling that for your students. And then the last bit of advice is avoid cynicism. These are some of the things I get to hear when I tell people I teach statistics.
Yes, great. Wait, is that Todd Snyder's song?
What?
You know, the Statistician's Blues?
Oh, I think I've heard it, yeah. That's some of the lines.
I
Yeah.
think so.
So there's actually a book called Lies, Damn Lies, and Statistics, which is a phrase attributed to Mark Twain, who attributed it to Benjamin Disraeli, who may not have actually said it, so that's kind of funny when it's talking about lies. But yeah, this is what I get to hear. And so I don't want the students to be cynical about everything, because as I mentioned before, there's a difference between trustworthiness and certainty. Every statistical test, every study has associated with it a level of certainty, and that is acceptable, and that is okay. And so we want students to recognize that, yes, this was based on a smaller sample size, and so we are less certain in our conclusions, but it doesn't mean that our conclusions are completely illogical. It just means we have to recognize the weight of this evidence because we are less certain. But it's the evidence we have available to us now. And so really keeping that framework for them, that social construct of numbers has been, I'll use them however I want, I can lie with them, I can make them do what I want. And that's where we start to get cynical about everything we read. And we don't have to be cynical, we just need to be critical. And then recognize that nothing is factual. I say that jokingly. Most scientific studies have a level of certainty attached, and that is what we have to recognize. And we want to teach our students. So I have a few resources. I will admit to taking and stealing quite a bit from Carleton College's Pedagogy in Action. They have some really great things, including using the spreadsheets like I mentioned before. So they have a lot of great things on activities and teaching materials, and then How to Lie with Statistics by Daryl Huff I mentioned, and then of course I have a few other books available. And I am of course available and happy to work with you on assignment design or thinking about your classroom and how to help teach your students evaluation of quantitative evidence.